Hi everyone, I'm recording this video to show you some of my answers to the review questions. So I'm not going to type them down, but I will go through all the questions one by one. Okay, so the first one, explain the Kenyan saber. Well, for the Kenyan saber, we are trying to use the labels from the nearest neighbors of a data point to decide the label of such a data point. So this is the idea of the Kenyan saber. So number two, does Kenyan saber work for multiple classes? And the answer is a yes. So for example, say if we have this kind of space and then we have the x and then we have some of the circles and then we also have some of the triangles. Okay, so we have three classes in this case. Well, and then if we have a question mark here, so can we make a decision on for the label of this question mark given we have some axes, we have some circles, and we have some triangles? And the answer is yes. So if we do the 1 nearest neighbor, and probably it will be x. So if you do like 3 nearest neighbor or 4 nearest neighbor, and probably you will still find that the closest samples are more likely to be x's, so this question mark will still be labeled as x. So number three, explain the training process of the Kenyan saber, and if we have more samples, what kind of the retraining is necessary? Well, if we have the data and the training, well, in Kenyan saber there's nothing to do. We just need to store the data. And if we have additional samples, well, for the retraining, we just have to put the data into the training set. So there's no additional things we have to do. Number four, explain the problem if we choose a very small or very large k value. So for this question, here are a couple of things well, we need to talk about. So number one, so if our data is imbalanced, and then we choose a value, well, a value that is high enough, the problem is the majority is going to win all the time. Say, well, do you remember once we talk about, say, we have 10 true and then 90 false. So, well, 10 positive samples and then 90 negative samples. And if we choose the k to be, for example, 21, and what is going to happen? So when k equals 21, and then the answer is the negative samples will win all the time. So this is definitely one of the problem, right? So, and then even though we want to choose we don't have such a unbalanced data set, and if you choose a small k, and the problem, say if you choose a k equals 1, the potential problem is still, well, we are learning from the mistakes, so we are overfitting the model. And for example, if you choose a large k value and k larger than necessary, for example, if you choose like say 50, well, if the data is not that the data is, we don't have so many samples, and then we choose a large value, and then we are over smoothing the model. So k very small value, we are overfitting the model, and k very large value, we are over smoothing the model. So number five, explain the process of choosing the best k value, and the answer should be the able method. And then if you forget about the able method, you want to take a look on the lecture notes again. So number six, how do you handle the categorical features? So there are three ways. So number one should be one hot encoder. Well, for the one hot encoder, and then well, the process is if we have n distinct values, and then for each of the distinct value, we are going to create a column just to encode the 0 and 1, saying if this feature present or missing. So this, the first one is one hot encoder, and for one hot encoder, and remember we are adding additional columns. And number two is label encoder. Well, this label encoder, and I would say this is done automatically. So, and then, well, sometimes we don't really want to have that. And for example, I have, for example, non-spicy, and we have mild, and we have spicy. Okay, so if we have those three labels, and well, for the if for the one hot encoder, and then we are gonna have non-spicy as a column, mild as a column, and spicy as a column, right? And then if you have the non-spicy, and then non-spicy will be a 1, and mild will be 0, spicy will be a 0. So this is one hot encoder. And for label encoder, and what we will do is say we can automatically map non-spicy to a 0, and then we map mild to 2, and then we have the spicy as a 1. So it is possible because the label encoder will do this work by automatically, so we don't have the control of the mapping. So if you say I don't like that, and then you can say a label is still a label encoder, but we want to use a dictionary. So this will be the third possibility. So we want to manually encode that. So in this way, we can control how do we want to map the values. So in this case, we can guarantee that we map the mild to 1, and we map the spicy to 2. Okay, so the next one, explain the naive Bayes in 1 or 2 sentences. So for the naive Bayes, and remember we are based on the Bayes theorem, right? So we are trying to study the probability distribution given the existing features towards the target labels, and then we want to use the joint distribution on the features of the given data point, and then we want to predict the labels. So number 8, does not naive Bayes work for multiple classes, or just a binary classification? So the answer is it can work for multiple classes. So for example, say we are given a person's look, for example, so we can collect this person's, say, hairstyle, and we also collect this person's for example, shirt color, and wear eyeglasses, yes or no, eyeglass, and then eventually we want to predict this person's job. Say this job could be, and for example, it could be a teacher, it could be a firefighter, it could be, for example, a salesman. Okay, so and then we are collecting those features, and then we will be able to predict how likely this person is going to be a teacher, how likely this person is likely to be a firefighter, and how likely this person is likely to be a salesman. So this model is definitely doable in naive Bayes. So naive Bayes can work for multiple classes. So number 9, the training process of the naive Bayes. So for example, well, what we have to learn is, say, for the hairstyle, it could be, well, long hair, short hair, or no hair, right? So for example, we want to learn the probability of long hair, and then the probability of the short hair, and the probability of no hair, right? So this is the probability that we can observe. And we can also observe, for example, the probability of a teacher, and the probability of firefighter, and etc. And then we can also observe some of the well, posterior probability. So for example, the probability of long hair given this person is a teacher, right? So and then the probability of well, no hair given this person is a teacher, etc. So in the training process, and we want to use our samples, and then we collect all those probabilities. So this is the training process. And if we have additional data points coming in as the training sets, and then unfortunately those probabilities will all be updated. So if we have new samples, we have to recalculate all those probabilities. So what's a potential problem which can lower the performance of a naive Bayes? For the naive Bayes, and I think I want to talk about two things. Number one, if we have a sample that we have not seen before, and then and our model is not able to make the prediction. So for example, in our new sample, the shirt color is, for example, purple. And then in our training data, we have never seen a shirt color to be purple at all. And then, in this case, we are not able to predict a sample who wears a purple shirt. And number two, and for naive Bayes, we are assuming that all the features are independent to each other. So if we do not hold this assumption, and then unfortunately, naive Bayes won't perform well. So number 11, do you need to worry about the dataset is imbalanced when using the k-nearest neighbor? And the answer is yes. And how about naive Bayes? So for naive Bayes, we don't have to worry about that too much. But if we only have, say, only one sample of teacher, this can still be problematic. So at least, if we have like 10 teachers, 10 firefighters, and then 100 salesmen, I think for naive Bayes, it is okay. But if we only have one teacher, it is still a problem. Explain the decision tree in one or two sentences. So for a decision tree, it is a sequence of the if and else conditions, and then it's similar to how we, the human, make the decision. So we check one condition, and then based on the result, and then we will move on and go to the second node and check the second condition, and then we will go on, and then eventually we can make a decision. So, if we do not specify any parameters when we train a trained model, what can be the problem? The problem can be, we are going to have a overfitted tree because we will go down and expand all the nodes, and it will stop when we have 100% pure node. So this will be a overgrown tree or a overfitted tree. So number 14, how do we get a sense of whether the dataset is beautiful or sloppy? The answer is exploratory data analysis. So, exploratory data analysis. So, usually we call this process EDA. So even before we build the models, we want to take a look on how beautiful the data is. And in this case, usually I want to try the pair plot if there are not so many features. Number 15, given a tree model and its visualization, how do we make a prediction? We just follow this tree from the top to bottom. So every node we visit, we will check the condition, and then we want to use the result to go down and visit the next condition. So eventually, we will go down from the top of the tree, that is the root, to the bottom. And then at the leaf, we should receive a class label. Okay, so why decision trees? Why in decision trees we do not need to normalize our data set? So it's not necessary because we normalize the data because we are measuring the distances between the samples. But in decision trees, we are not doing that, so it's not necessary. So number 17, in naive Bayes, what's the risk if we have too many features in a data set? So if we have too many features in the data set, it's more likely that some of the features are not independent to each other. So for example, if we have the people's weight, and then whether this people has high blood pressure problem or not. So those are the two features. So people's weight as one feature, and then high blood pressure problem. Okay, so the weight is a numerical feature, and then high blood pressure problem is a yes or no feature. And then those two features are, I assume that they are not really independent to each other. So when we have this kind of features, and then it's more likely that if we use the naive Bayes, and then the performance won't be that good. Okay, so 18. do we normalize the data for naive Bayes? And the answer is no, it's not necessary, because again, well, for the naive Bayes, we are not measuring the distances between the samples. So what are the different approaches of creating big number of the members in a voting classifier? So, well, there are 3 different approaches. So number 1, well, different models, right? So if we want to have a decision tree, a logistic regression, and a k-nearest neighbor, and they are different models. So well, we can do independent committee members, but it will be hard for us to do 100 committee members. So what's the second one? The second is train the same type of models with a different subset of data. So for each of the committee members, we only give the committee member a small portion of the data set. So well, so each of the committee members, even if they are using the same algorithm, but they receive different data set, so they're still independent. And what's the number 3? So number 3 is a decision tree variant. Oh, sorry, it's a random forest variant. So give small portion of features. So when we train each of the committee member, we don't give the committee member all the features. We only give a small portion of the features. So this again can guarantee that each of the committee member, they receive different training. So well, because in this case we are saying we are aiming on a high number of the committee members. So the first one may not work that well, but the 2 and 3, those are the 2 fine ideas for training 100 voting classifier committee members. Okay, so the last one, discuss the difference between in building a random forest with 100 trees, and then a AdaBoost model with 100 trees. So I think the number 1 thing is the strategy of building those trees. So strategy of building trees. So well, and because for random forest, and we are just building all the trees all random, well, all in parallel. So we can use, if we have say 100 cores, and then we can have each of the core build 1 tree at the same time. But for AdaBoost, the trees are built in sequence. So we have to finish the first tree, evaluate that, and then change the weight of the samples, and then build the second tree. So the strategies are different. And then we can also talk about the features used. So well, in random forest, and then we only use well, a small portion of the features to build each of the tree. But in AdaBoost, well, we can consider all the features, right? And then number 3, the height of the tree. So well, in random forest, and is it possible that we have the trees that have a height for example 3, or a height of 5, and is it possible? But how about AdaBoost? So for AdaBoost, and by default, we are creating the tree stumps, right? So for AdaBoost, and then for each of these decision tree, they only split once. So those are at least the 3 differences between AdaBoost and random forest, even though they both have 100 trees in their collection of the committee members. Okay, so those are some of my review questions, and I hope this can help you. Okay, bye bye.